Hi everyone, welcome back to the channel. Today we have another comprehensive review on thermochemistry. So question 1, a sealed styrofoam coffee cup containing a reaction mixture is best described as which type of system? So we have open, closed, isolated, and adiabatic system. So adiabatic system just means that there is zero heat being lost or gained from it. And we can't know this from knowing that it's a styrofoam coffee cup, so we can eliminate this. So an open system has exchange of materials and energy. A closed system does not have exchange of materials, but it can exchange energy. And then an isolated system cannot exchange either materials or energy. So which one is a sealed styrofoam coffee cup? This is a closed system. Because it is sealed, it cannot exchange materials. If it were open, for example, and maybe some gases were released, it would be able to leave the system, and that would be an open system. But in this case, it's sealed, so it can't exchange materials, but it can exchange energy. And then an isolated system would be something like a bomb calorimeter, where energy cannot be exchanged with the surroundings. So this is a closed system. Next, question 2. A gas absorbs 150 joules of heat from its surroundings and has 60 joules of work done on it by the surroundings. What is delta U for the gas? So our very important formula is that delta U equals Q plus W, or heat plus work. So we just have to use this to calculate it. So it is absorbing 150 joules of heat, which means it is a positive value. And then 60 joules of work that is done on it by the surroundings. So because it's work done on it by the surroundings, it is gaining work. The system is gaining work, so it will be another positive 60. So basically we add these two up and we get 210 joules. Okay, next, which of the following correctly describes photosynthesis? Photosynthesis, as we know, requires energy. And what is this energy that it requires? Well, it's sunlight. So if it requires sunlight, it requires energy, and this makes it endothermic. And then endothermic reactions always have a delta H above 0, and then exothermic below 0. So this will be option B. Okay, question 4. Which of the following is a state function? Remember that state functions do not depend on the path that is taken. So both heat and work depend on the path, but enthalpy does not. It's a state function and it only depends on what we start with and what we finish with. Next, question 5 for the reaction. At 298 Kelvin, what is the pressure volume work done? So we know that the formula for work is negative P delta V. But then I'm looking at all the answers and they have like RT here. So I know that we have to convert this to the other version of the formula. So if we recall that PV equals nRT, and then we isolate for V, V will be nRT over P, and then we can sub this back into the formula here. So it'll be negative P times delta nRT over P, and then we can cancel the P's out. So then work will be negative delta N of the gases times RT. And then now we can use what we know from this equation. So we have negative RT, and then for the change in moles of gas, we end with 2 moles of gas, but we started with 4 moles of gas. So it'll be 2 minus 4, or it will be negative RT times negative 2. and then this will give us answer A. So we didn't even have to calculate what the actual value was, but you could calculate if you want to, and you'll get 4958. And this makes sense because it is the only positive value, and if it's positive, it means that we are losing gas and work is done on the system by the surroundings. So we technically didn't really have to calculate this anyway, we could just look at the sign. Okay, question 6, a 200-gram iron sample with a specific heat capacity of 0.449 at 95 degrees Celsius is placed into a 150-gram of water at 20 degrees Celsius with a specific heat capacity of 4.18. What is the final temperature? So, a very important thing to know is that the Q of iron will equal the negative Q of water. And this is because whenever you have a system and a surroundings, the Q values are going to be the opposite sign of each other. So Q system equals negative Q surroundings, or in this case, we have iron and water. So what is the Q of iron? Well, we know that Q equals MC delta T. So for iron, we have 200 grams. The heat capacity is 0.449. And then the change in temperature, well, we don't know the final temperature, so we'll call it T2, but we know the initial is 95 degrees Celsius. And then if we simplify this, we'll get 89.8 times T2 minus 8531. And then let's do the same for water. So Q water equals MC delta T again. We have 150 grams, 4.18. And then for the temperature, because the iron sample is being placed into water, the final temperature is going to be the same for both the iron and the water. So we'll have the same final temperature. So I can write T2 again, minus the initial, which is 20 degrees Celsius. Simplify this out and we'll get 627 times T2 minus 12,540. And then because I'm going to go back to this first formula here, we can say that the Q of iron equals negative Q of water. So I'll put a negative here, and then in brackets, we'll put the calculation that we got. And now we just do the math. So this will be, we'll isolate for T2. And then you should get 29.4 degrees Celsius. And that is the final temperature. Okay, question 7. In a bomb calorimeter experiment, which relationship is correct? So an important thing to know is in a bomb calorimeter, there is constant volume. So if we know this key thing, and we know the formula that delta U equals Q plus W, and then we also know that W is negative pressure times change in volume. Well, we know that it's constant volume, so then delta V will be 0, and then multiply by pressure, so all of this will be 0. And now we're just left with delta U equals Q. And then we can write the subscript here. If you see a subscript like QV, this just indicates that it's constant volume. So delta U equals Q at constant volume, which is option B. Okay, when 5 grams of NaOH with a molar mass of 40 grams per mole dissolves in 95 grams of water in a coffee cup calorimeter, the temperature rises from 22 degrees Celsius to 34.6 degrees Celsius. What is be delta H per mole of NaOH. So we know delta H is heat of the reaction divided by the moles. And we know this because in all of our options, we can look at it and it's all in kilojoules per mole. So that means our equation should be correct. And then I'm going to look at the temperatures. So we have an increase of temperature. And then when the temperature increases, it is an exothermic reaction because we're releasing energy. So because it's exothermic, I know that delta H is below 0. So I have to stick a negative sign in front of the formula because we'll have a negative Q of reaction. And then just like before, we know that Q is MC delta T divided by moles. And then now we can just plug in our values. So negative, the mass will be 5 grams from the NaOH plus the 95 grams from the water. Specific heat capacity is 4.18, always with water. And then change in temperature is 34.6 minus 22 over the moles, which is, we have to do a small calculation on the side here. So moles equals mass over molar mass. So we have 5 grams of NaOH divided by 40 grams per mole. So we have 0.125 moles of NaOH. And then all we have to do is calculate this, and we'll get negative 42,134.4 joules per mole, and then convert it to kilojoules by dividing by 1,000, and we'll get negative 42 kilojoules per mole, which is option A. Next, question 9. What is the total heat required to convert 25 grams of ice at negative 10 degrees Celsius to steam at 120 degrees Celsius? So this is quite a long process, but we have to break it down into different phases. So we have two different transition states, I guess. So we have one, which is going from ice to water, because it has to become water in order to become steam. And this ice starts at negative 10 degrees Celsius, and it will turn into water at 0 degrees Celsius. And then we have phase 2, which is water converted to steam. So water will start at 0 degrees Celsius, and then we end up at 120 degrees Celsius. So let's break down each of these steps and then calculate the heat required for each of the steps, and then we'll add it all up at the very end. So Q1 is going to be the heat required to heat the ice from negative 10 degrees Celsius to 0 degrees Celsius. So I'll write here that the phase is ice. So this is MC delta T. So we have 25 grams, and then we have to look. So the specific heat capacity of ice is 2.09. And then the change in temperature, we end at 0 and we started at negative 10. So calculate this and we'll get 522.5 joules in this very first step. And then we have another step. So there's two different categories of heat required here. The first one is changing the temperature while it stays at the same state. And the other one, where we use the delta H of fusion is for when it's changing states, but the temperature doesn't change. So our next step will be going from ice to water. And this we'll call it Q2. So for this step, Q is delta H fusion times the number of moles. It tells us here that it's 6.02. And then how many moles do we have? We have 25 grams. And then we have to divide by the molar mass, which is 18.02. This will give us 8.35 kilojoules. And just be careful of the units. This one's in kilojoules because the fusion, the value that they gave us was in kilojoules, but for the other one, it's in joules. So just remember to convert all of your values properly at the end. Okay, so now we have water. The third step is heating that water from 0 degrees Celsius to 100 degrees Celsius when it turns into steam. So this will be Q3, which is also MC delta T again. So we still have 25 grams. And then now we want to use the specific heat capacity of water, which is 4.18. And then the final temperature will be 100 degrees Celsius, and we started at 0. So this will give 10,450 joules. Okay, step 4. Now we want to go from water to steam. So this will be Q4. So we have change in enthalpy of vaporization. Remember that fusion is from solid to liquid or liquid to solid, and then vaporization is for gas to liquid or liquid to gas times the moles. So this is 40.7 times mass divided by molar mass, and we'll get 56.47 kilojoules. And then the final step, so we have steam now, but we still have to heat this steam from 100 degrees Celsius to 120 degrees Celsius. So this is our final step, I promise. So Q5 is also Q equals MC delta T, so 25 times 1.996, and then 120 minus 100. And this is 998 joules. So those were all the steps, and now we just add it all together. So total heat, and because all of our values are in kilograms, I'm going to convert, oh sorry, not kilograms, kilojoules. I'm going to convert all the joules into kilojoules by dividing by 1,000. Or we can just move the decimal place 3 places to the left. So 0.5225 plus 8.35 plus 10.45 plus 56.47 plus 0.998 equals 76.8 kilojoules. So option C. So if you're still confused about this, just remember that in the lecture slides, we have a diagram like this. It looks like this, right? So just know that for like these calculations, it's like this slanted line, and then for the calculations where we have to use change in enthalpy, it's like this part of the graph. Okay. Question 10. Using bond energies, estimate the change in enthalpy of the reaction and they give us all of the bond energies that we need. So delta H of the reaction equals the sum of BDE, the bond dissociation energy, of the reactants minus sum of BDE of the products. Or you could think of this like some people call it bonds broken minus bonds formed. So it tells us our formula, but I think an easier way to visualize the different bonds that we have is just draw it out really quickly. So H2 gas is an H bonded to an H, plus Cl2 gas is a Cl with a single bond to another Cl, and then 2 HCl is an H single bonded to a Cl. So we can see it clearly now. So for the reactants, first we have H to H, which is 436, plus Cl to Cl, which is 243, minus, we have to put the 2 in front because we have a coefficient of 2, and then H to Cl is 432. And then if you calculate it, you get negative 185 kilojoules, which is option A, because it's negative. Okay, question 11. Which of the following correctly defines a standard enthalpy of formation? Standard enthalpy of formation basically just means change in enthalpy when you form 1 mole of product with all standard states. So this is option B. Question 12. Using standard enthalpy of formation values, calculate delta H reaction for this reaction, and then given all of the enthalpies of formation. So this is kind of similar to the question with the bond dissociation energies, except there's just a little change in the formula. So our formula looks like this. It's the sum of the delta H of formation of products minus the sum of the reactants. And then this symbol here just is the coefficient. So if it's a bit confusing, just remember that it's usually reactants minus products, or bonds broken minus bonds formed, except when you're dealing with enthalpy of formation. That's when it switches and it's products minus reactants. I think that it's the only time when it's products minus reactants. So just remember, formation is the one that's the other way around. So on the product side, C2H6, so that is negative 84, minus, for the reactants, we have C2H4, which is 52.4, and then H2 gas is 0. And then we get negative 136.4 kilojoules, which is option A. Question 13. Given Formula 1 and Formula 2, what is delta H for the final formula? So this is, in my opinion, probably one of the more fun questions, and it's kind of like solving a system of equations in math, but how I like to do it, by the way, I have a whole other video on this. It's the very first video I uploaded. I like to write out all the equations that they gave us, just so it's like stacked on top of each other. So I kind of look at it like a system of equations, like in math, and then I just write delta H on beside it. So first one, negative 198 kilojoules. Second one, negative 792 kilojoules. And then I just draw a line and then I write the final formula below it. I'm not going to write the states. So we need to tweak our top two formulas in order to get the last formula on the bottom. So I find that the easiest way to do this is to look for the species in the final equation that only appear once in all of the other equations. So for example, I see that there's sulfur here, and sulfur only appears once in our second formula over here. So this automatically tells me that I have to keep sulfur on this side, so I don't flip the equation anyway, but I have to just divide it by 2 because I have a coefficient of 2 here and a coefficient of 1 here. So after I do that, I'll write it underneath. I have S plus 1.5 O2s and then SO3. So what I do with the delta H is I divide it by 2. So that equation is done now because the S is perfect. What I need to do now is deal with the top formula. So I actually see that there's another species that only appears once, and that's SO2, and it only appears once over here. So SO2 ends up on the product side, but over here I have it in the reactant side. So one thing I have to do is flip the equation, and then I also see that it has a coefficient of 2 here and 1 here, so I also have to divide this by 2. So I have to do 2 things to the top formula. And then that will give me the formula on the bottom. So I know everything I need to do now. So delta H will be like all of the delta H's summed together. So for delta H1, I flip the equation. So that means I have to add a negative sign in front. And I write the value, and then I also divided it by 2. So I divided by 2 plus the second delta H, and then for this one I just divided it by 2. So I do that, and now I can calculate it, which will give me negative 297 kilojoules. If you want more practice, once again, I have a whole entire video just on solving these types of questions. Okay, so I'm looking back and I realized I never really showed you guys exactly how the last equation even like comes to be. So I'm gonna write out like all of like the new formulas after we did all these changes to it. So once we flipped the top formula and divided it by 2, we will get SO3 and then SO2 plus 0.5 O2. Yes, you can have decimals as coefficients. And then for the second one, I already kind of wrote it there, but I'll write it again. S plus 1.5 O2 SO3. So one thing is that when a species, for example, SO3, when it appears in both formulas but on opposite sides, you can cancel them out. So these will kind of like subtract each other out. But when they're on the same side, you would like add the coefficients together. So in this case, I don't have anything like that, but I'll show you with the O2. So these O2s are on opposite sides. I have 0.5 here and 1.5 here. So because they're on opposite sides, I subtract them, and then 1.5 minus 0.5, I would be left. So like this one would be gone on this side, but then this one I would subtract 0.5 from it, and I'll just be left with 1. So our final equation will be S plus O2, and then I'm left with SO2 on this side. And then that's the same as the equation that they wanted. So on opposite sides, coefficients minus each other. On the same side, they add each other. And then if you're still confused, you can find more in the other video. It's titled like Hess's Law Problems, and it'll make more sense when you watch that. Okay, question 14. When applying Hess's Law, if you reverse a reaction, what happens to its delta H? We just did this above. If you reverse a reaction, you just change the sign. So it's option C. Question 15. Based on the heat of combustion per gram, which fuel releases the most energy per gram burned? So when we release the most energy, we look for the one that's the most exothermic, or the one with the most negative value, which is hydrogen. Question 16. A system undergoes an adiabatic process in which 300 joules of work is done by the system on its surroundings. What is delta U? So once again, write out our golden formula, which is delta U equals Q plus W. A very key thing to note in this question is that it tells us it's an adiabatic process. Adiabatic process means that Q equals 0. There's no heat being gained or lost. So this was very helpful for us because if we know that Q is 0, we can just focus on work. And it says that work is done by the system on its surroundings, which means that work is leaving the system and work is negative. If it were the other way around, so it's always if the system is doing work on its surroundings, work is negative, and if the surroundings are doing work on the system, then it's positive. So in this case, work is negative, and then because this is 0, work is the only thing that determines the sign of delta U. So if we know it's negative, we know it has to be negative 300 joules. Hopefully that made sense. Okay, question 17. Which relationship correctly connects delta H and delta U at constant pressure for a gas phase reaction? So the formula that is given to us is that delta H equals delta U plus pressure times change in volume. And then this is not true because it has to be change in volume. So we have to convert it to the other form where we use PV equals nRT. So just like we did before, pressure equals nRT over V, or you could also isolate for V. I don't think it really matters. So this is delta U plus sub this in for P, nRT over V times delta V. And then these can cancel out. And then you're left with delta U plus nRT. Or you can put, you can just put the delta in front. So this is option A. And then the last question, which of these substances would you expect to have the lowest specific heat capacity and why? So specific heat capacity depends on 3 things. Number 1, movement of a whole atom or a molecule. So the larger the molecule, the more atoms it has and the more it will move. So basically a bigger atom or bigger molecule will have a higher specific heat capacity. Number 2 is the internal motions or degrees of freedom. And a higher degree of freedom is a higher specific heat capacity. Degrees of freedom is basically just like how many different ways the molecule can move internally. Like how many different ways can it be rearranged in different positions and things like that, like resonance structures. And then the last thing it depends on is intermolecular forces. The stronger the intermolecular force, it will have a higher specific heat capacity, right? Because it's more difficult to break those forces and evaporate it. So if we look at all of our options, H2O, because it has strong hydrogen bonds and many internal degrees of freedom, this would mean that it has a high specific heat capacity. Iron, because metals have a simple lattice structure with few degrees of freedom. Well, this will have the lowest because remember that we want complex structures with a lot of degrees of freedom. So this should have the lowest specific heat capacity, but we can look at the other options. So for ethanol, because it's a larger, more complex organic molecule, remember that a larger and more complex molecule will mean a higher specific heat capacity. And then ammonia, because it has a lone pair that stores extra energy. Remember that extra energy means higher specific heat capacity. So it is iron. So those were all the questions. Thank you guys for watching, and I'll see you in the next video.